Somewhere in our galaxy, there is an object that could kill you from 1,000 kilometers away, without ever touching you. It is smaller than a city. You could cross it in 20 minutes if crossing were possible on a surface where a single misstep would flatten you into a film 1 atom thick. It is the crushed corpse of a star far larger than our sun, and it is still spinning, hundreds of times every second, sweeping the darkness with beams of light like a lighthouse built by physics gone mad. Fall toward a black hole, and it lets you vanish quietly past an invisible edge. Fall toward this, and it makes you arrive, at half the speed of light, against something solid. This is a neutron star, and it is, in almost every way, deadlier than the black hole beside it. To understand it, forget the word star. What waits for you here is what a star becomes after it dies badly. When a giant sun, 8 to 20 times the mass of ours, burns through the last of its fuel, its core can no longer hold itself up. In less than a second, a ball of matter wider than the Earth collapses to a sphere about 20 kilometers across. The outer layers rebound and detonate as a supernova, briefly outshining an entire galaxy. But the core keeps falling inward until the very atoms are crushed. Electrons are rammed into protons, and what is left is a single, city-sized ball of almost pure neutrons. The physicist James Chadwick discovered the neutron in 1932. Just 2 years later, Walter Baade and Fritz Zwicky predicted that a star could be built entirely from them. Almost nobody believed it, until 1967, when a young astronomer named Jocelyn Bell Burnell found a signal in her data ticking with impossible precision. The dead stars were real, and they were talking. Here is the number that breaks the mind. A single spoonful of neutron star matter would weigh about 1 billion tons, as much as a mountain. It is a place where matter itself has been forced into a state it can take nowhere else. You are falling toward the densest thing in the universe that still has a surface to hit, and so you fall. Unlike a black hole, this object does not hide. It blazes. Its surface glows at hundreds of thousands of degrees, far hotter than the sun, pouring X-rays into space. And as it spins, its magnetic poles fling out twin beams of radiation that sweep past you like the beam of a lighthouse. If one of those beams happens to point at Earth, we see it flicker on and off with each turn. We call these pulsars, and this is exactly the ticking Jocelyn Bell Burnell found in 1967. The spin is difficult to believe. A young neutron star can rotate dozens of times a second. The fastest one we have ever found turns 716 times every single second. Its equator moving at nearly a quarter the speed of light. A sphere heavier than the sun, spinning faster than a kitchen blender, and almost perfectly smooth. Its gravity bends light so sharply that you can see part of the star's far side curving into view around its edge. A world turned partly inside out. From your vantage point, falling closer, it is not a gentle glow. It is a strobe of hard radiation, brightening as you close the distance. Long before you feel its gravity tear at you, its light alone is enough to cook you. Suppose for a moment you could ignore the radiation. What would it be like to simply stand there? You could not. On the surface of a neutron star, gravity is roughly 200 billion times stronger than on Earth. Your body would not fall so much as cease, pressed instantly into that impossibly hard crust with a force no material could survive. The mountains here tell the story. The surface of a neutron star is one of the smoothest things in existence. Its tallest peaks may rise only a few millimeters because gravity flattens anything taller. And that crust is not ordinary rock. Beneath it, nuclear matter is squeezed into strange shapes that physicists nickname nuclear pasta, sheets and tubes and knots that may be the strongest material in the universe, perhaps 10 billion times stronger than steel. The star bends time as well as space. Clocks on its surface run noticeably slower than yours, and light climbing away from it loses energy, its color dragged toward the red. To escape this surface, you would need to travel at roughly half the speed of light, which means the reverse is also true. Anything that falls here, a rock, a spacecraft you, arrives at that same unthinkable speed. But you will never reach the surface intact. Long before it, the star does to you what a black hole would. And it does it in the open, with nothing hiding the act. Because the object is so small and so dense, its gravity changes savagely across even a short distance. If you fall feet first, your feet are pulled far harder than your head. The difference stretches you, head to toe, into a thinning thread. Astronomers call it spaghettification, and here it happens not past some hidden horizon, but out in plain view. Kilometers above a surface you can still see glowing beneath you. By the time what remains of you meets the crust, you are no longer a body. You are a stream of atoms, striking the densest solid in the cosmos at over 100,000 kilometers a second. The impact releases a flash of energy, a brief bright scar on a star that will not even notice you arrived. A black hole erases you privately. A neutron star executes you in the light. And yet gravity is not the cruelest thing about some of these stars. There is a rarer, stranger kind, and its true weapon cannot be seen at all. A small fraction of neutron stars are born with magnetic fields of monstrous strength. We call them magnetars. The magnetic field of a magnetar can be 1,000 trillion times stronger than Earth's, the most powerful magnetism known to exist anywhere in the universe. At that strength, magnetism stops being a subtle force and becomes a blade. Come within 1,000 kilometers of a magnetar, and its field would distort the very atoms of your body, stretching their electron clouds into thin rods, dissolving the chemistry that holds you together. You would be unmade not by being crushed or burned, but by having the shape of your atoms rewritten. We have felt their reach from across the galaxy. In December 2004, a magnetar called SGR 1806 released a single flare that in 1/5 of a second poured out more energy than our sun gives off in 250,000 years. It struck Earth's upper atmosphere from 50,000 light years away, from halfway across the Milky Way, and we measured it, a dead star reaching out through space and touching our sky. These corpses are not quiet, they are not finished. Our galaxy alone may hold 100 million of them, most long gone dark and silent, drifting unseen between the stars. Their crusts crack. As a neutron star ages and its spin slowly winds down, stress builds until the surface fractures in a starquake. A shift of perhaps a millimeter that unleashes bursts of radiation and briefly changes the star's spin. Some flicker and glitch, betraying the strange superfluid ocean hidden beneath their crust. And sometimes two of them find each other. When a pair of neutron stars spirals together and collides, the universe forges something precious. In that final instant, in the debris flung from the wreck, atoms heavier than iron are born. Gold, platinum, the rare metals of the periodic table. In 2017, we watched exactly this happen. A collision detected first as a ripple in space itself, a gravitational wave, and then as a fading glow. Much of the gold in the ring on your finger was likely made in the death crash of two dead stars. They kill without touching. They shine without living. And in dying a second time, they seed the galaxy with treasure. We tend to imagine death as an ending, a light going out. A neutron star is the universe's argument against that idea. It is what remains when a sun is crushed out of existence, and yet it is brighter, faster, denser, and far more dangerous than the living star it once was. It spins in the dark hundreds of times a second, sweeping its beam across a galaxy that has already forgotten the star it used to be. It flings its magnetism across 50,000 light years to brush against our sky. It is a corpse that still burns. The universe, it turns out, does not always bury its dead. Sometimes it winds them up and lets them keep score.